Our next lesson in the unit gas laws is going to be gas laws number 1. In this lesson, we're going to look at several things. We're going to look at standard temperature and pressure, at the idea of the ideal gas, what that is. We'll look at 3 laws. We'll look at Boyles Law, Charles' Law, and Gay-Lussac Law. And we'll look at temperature and absolute temperature and temperature unit conversions as part of what we're doing here. So first topic, standard temperature and pressure. Oftentimes, whenever a scientist is doing an experiment, if he's doing an experiment with gases, is that his particular laboratory or her particular laboratory is going to have certain conditions. There'll be a certain pressure, there'll be a certain temperature, and so on and so forth. Now, we know that the way that a gas behaves depends on what its temperature and what its pressure is. The higher the temperature, the higher the pressure is, and so on and so forth. There are many, many things that sort of involve whatever you're measuring a gas, but temperature and pressure pretty much are going to affect what a gas does. If I'm trying to reproduce that experiment somewhere else, then what I find is that my conditions are different than their conditions. And so it's very difficult to compare two experiments done in 2 different places. As a result, basically, the different conditions of pressure and temperature, scientists have come up with this idea of creating a standard temperature and a standard pressure, something that will say that we'll always adjust the numbers that we take in our data to the standard temperature or the standard pressure. So everyone will have a common reference. And so standard temperature is defined as being basically 0 degrees Celsius. In Kelvin, which we'll talk about in a little bit, it's 273.15 Kelvin. And so that's defined as standard temperature. Standard pressure is 1 atmosphere, or 760 millimeters of mercury, 101.3 kilopascals, 760 torr, 101,300 pascal, all those ones we talked about more recently. Just as a note, there are a couple different standard temperatures and pressures out there. The one we're using here is going to be the National Institute of Standards and Technology, a NIST standard. There are other standard temperatures and pressures out there, but this is the one that we're going to be using for this class right here. Now, if we have a gas that is adjusted so it is both at 0 degrees C and at 1 atmosphere, where it has both standard temperature and standard pressure, that gas is called at STP. That is at standard temperature and pressure. And so if you ever see something that says that, okay, you have 5 liters of a gas at STP, you have 5 liters, the temperature is 273.15 Kelvin, the pressure is 760 millimeters of mercury. You know those things automatically. And so this is sort of what we start off with here. Let's take a look at an ideal gas, what that is. To talk about first, we want to talk about gases. In solids, we know that the particles are basically very, very close to each other, so that the forces between the molecules, these intermolecular forces, sort of rigidly hold the atoms together. In a liquid, the particles are usually a little farther apart. And so the intermolecular forces are weaker, but still sort of dominant. The atoms as they go by each other will interact with the other atoms. They'll affect the other atoms as they go by. It's sort of, we sort of said like shaking hands as they go by here. They do exert a force, but it's a very short force. Now, in gases, the particles of a gas are generally very far apart. And since they're very far apart, they don't generally exert forces on each other very often. It would sort of be the equivalent of if we were to start just randomly throwing grains of sand around the room. The chances of 2 grains of sand running into each other is pretty low. It may happen sometimes, but it doesn't happen very often. And so we can say this. In gases, particles are far apart. They rarely interact with each other. If we were to assume that those particles never interact with each other, this idea that a gas where the particles never interact with each other, they don't run into each other, don't exert forces on each other, is called an ideal gas. And this is an important concept. And the reason why is, we'll sort of talk about this in a second, but basically in an ideal gas, since the particles never interact with each other, then we only have to worry about them interacting with the surface of their container. And so in finding the pressure, that we don't have to worry about some other little details about what happens when the gases run into each other. All we worry about is what happens when it reaches its container. And so if we only worry about what happens when the gas hits the container, then the gas laws we have are very simple. And so these are the types of things that we're basically going to use in this class. So the particles, since the particles never interact with in an ideal gas, the laws are very simple. And so we're going to use gas laws that assume an ideal gas in this class because of the simplicity and the fact that, as we said before, in most everyday gases, the particles are far apart and they don't interact very often. And so the exception to this, and this is sort of the third point right here, is that gases that have a very high density don't act like ideal gases, because if they're very high density, that means there are a lot of particles crammed together, and the more particles crammed together, the more likely they are to impact each other and to exert forces on each other. And the separate thing is that gases at very low temperatures typically don't act like ideal gases as well, because the particles are going very slowly. So if they ever do interact, since they're going very, very slowly, there's a big it's a big thing. It's sort of like this: is if I'm going very, very fast and someone throws a grain of sand at me, it doesn't really affect me that much because I have a lot of energy due to my speed to start with. If I was trying to be as still as possible and someone threw a grain of sand at me, it might make me move a little bit because of the fact that I'm going very slowly to start with. And so gases that have very high densities or very low temperatures are not ideal gases. And so the ideal gas laws that we'll talk about here, all the gas laws we're going to talk about in this class, don't work for those types of gases. But for everyday gases, like the air that's in your room, and or ones with high temperatures or low densities, then these gas laws work very well, and we can assume that the gas is basically an ideal gas. And so that being said, let's take a look at some of our gas laws. And I didn't mean to do that. All right, our first gas law is called Boyles Law, and it deals with this. Let's suppose that we had a balloon, and I'm going to take the balloon and I'm going to squeeze it in so that I have reduced its volume. So we're reducing the volume of the balloon here. And the question is, what happens to the pressure? And so if I squeeze a balloon in, then the particles are going to be closer together. If the particles are closer together, then it means that there'll be more impacts with the surface. And if there are more impacts with the surface, then we'll have a higher pressure. And so we could sort of say this, is if I start off with sort of a certain balloon, it has a volume of one thing, a pressure of another thing, and if I take the volume and I make the volume go down, then the pressure in response is going to go up. Now, this means that pressure and volume are inversely proportional. If we're trying to set up an equation as to what happens when you change a gas, that I have a gas that's existing with a certain pressure, a certain volume, and I change the volume or I change the pressure, and the two things are inversely proportional like they are right here, the equation that we're going to use is this one right here. P1 times V1 equals P2 times V2. That is the original pressure, the pressure at the first bit, times the original volume, the volume at the first bit, equals the pressure in the second part after we've changed the gas, times the volume in the second part. That is after we've changed the gas. This is Boyle's Law. P1 V1 equals P2 V2. And so if we said that we start off here with a gas that has a pressure of, we'll say, 10 atmospheres, and we start off with and it has a volume of 2 liters. And let's say that what we're going to do is we're going to squeeze the gas in so it now afterwards only has a volume of 1 liter. So we have sort of like before here, and we have after right here. And we're trying to find the before and the after. What we do is we say, okay, what's the pressure before? That's P1. Pressure before is 10 atmospheres. Times, what's the volume before? The volume before is 2 liters. So we've got that here. This is going to equal the pressure after. Well, we don't know what the pressure afterwards is. That's what we're trying to find. So we say P2 right here times the volume afterwards. That's 1 liter. And so doing this, we say 10 times 2 is 20. So 20 equals basically P2 times 1, so it's P2. And so in this case, the pressure must be 20. The unit's going to be atmospheres because liters canceled on both sides. I only have atmospheres remaining. And so that's basically how Boyle's Law works. For Boyle's Law, we can use any unit of pressure or volume that we want to. The only thing is that whatever you use for your pressure on one side has to be the same unit as the pressure on the other side, and whatever unit of volume used on one side has to be the same unit of volume on the other side. If I want to use my pressure in torr over on this side, I just have to use torr over here. If I use even non-standard, non-metric units, like I could use gallons for volume here, and if I did that, I just have to make sure it's gallons over here on the other side. And so basically that's how Boyle's Law works. And so let's see what happens with an example on that. So let's do a Boyle's Law problem here very quickly. And so to do that, so a sample of hydrogen gas at 735 torr is found to have a volume of 215 milliliters. If the gas is allowed to expand to 285 milliliters without a change in temperature, what is the pressure of the gas? So what you want to do is you want to figure out first what are our original, so what's our original pressure, our original volume, and then we want to find what our final pressure is and our final volume. And let's see what we know about these things. So do we know the pressure to start with? A sample hydrogen gas at 735 torr. So we know the original pressure, 735 torr. Okay. Do we know the original volume? Yes, 215 milliliters. So we tell you 215 milliliters. Okay. Do we know the pressure afterwards? If the gas is expanded to 285 without a change in temperature, what is the pressure? No, we don't. That's going to be what we're looking for. Do we know the final volume of the gas? Yes, it's expanding to 285 milliliters. So we'll set up our equation here. Our Boyles Law says P1 V1 equals P2 V2. And so original pressure here is 735. Yeah, that's not what I wanted. Get rid of that. So 735 torr times V1, which is 215 milliliters, equals P2, which we don't know, times the V2, the volume, 285 milliliters. Okay? And so if you get out your calculator here, that we'll work on, say, the left side here. And so doing that, we get 735 times 215. And when I do that, I get 158,025. No rounding yet because we haven't gotten to the answer yet, is equal to 285 times P2. Divide both sides by 285. And when you do that, we get a total of 554.47. Significant figure-wise, we have 3 significant figures here, 3 here, 3 here. And so as a result, our final answer will have 3. And so our answer here would be 554. What unit do we want to use? Well, the unit of pressure that we have here is going to be the same as the unit of pressure we had before. And so since we don't know this one right here, then we have to look over here. So the pressure we had over here was in torr. That means that our answer is going to be in torr. Notice also we made sure we had the same unit of volume on both sides, milliliters on both sides there. And so our final answer for the pressure is 554 torr. Now let's see if this makes sense. We started off with a pressure of 735 and a volume of 215, is that the gas expanded to 285. And so if the volume expands, then we would expect that there's a less dense gas, there are going to be fewer impacts on the surface, and so the pressure would be lower. And so we went from 735 down to 554, so sure enough, the pressure got lower just as we expected. So this is how you'd go about using Boyle's Law. So let's look a little bit at temperature. So we know this, that as the temperature decreases, temperature of a gas decreases, the kinetic energy of the particles is going to be lower. That means the particles are going to be moving more slowly, and so when they hit the sides of the container, they're not going to put as much of a force because they're moving slower. And if the force is lower, that means the pressure is lower. So as the temperature of a gas decreases, the pressure decreases. So what happens if the temperature is 0? Normally, 0 means like none, right? And so if we had no temperature, wouldn't that sort of imply we had no pressure? But it's pretty clear that, the temperature can be 0 degrees outside and we don't all suffocate because there's no air pressure. There's certainly still air pressure there. And so we sort of got a little problem. In addition, what happens if the temperature is negative? What does it mean to have a negative temperature? I mean, the particles are moving negatively? That doesn't really make much sense. There's sort of a problem with the temperature scales that we use normally. When you look at Fahrenheit and Celsius, is that Fahrenheit, Celsius are what we call relative temperature scales. And so a relative temperature scale is basically one that is, the numbers that are there are relative to some other number. In this case, 0 degrees. On the Fahrenheit scale, 0 degrees is picked because it's a particular temperature of a saltwater mixture, salt-ice mixture. And so that's why they pick that. For Celsius, 0 degrees is the freezing point of water. Those zeros, while they have a reason why they're picked, really have nothing to do with the actual movement of molecules. The freezing point of water is not the point where all motion of molecules stops. So it really isn't a true zero temperature. A zero thermodynamic temperature is the technical term for it. And because of this, to show that these temperature scales, that Fahrenheit and Celsius, are not absolute temperature scales, ones where zero actually means zero temperature, is that they use degrees. That's the reason why you have, degrees Celsius or degrees Fahrenheit. It's basically saying that this is a comparison to something else. It's a relative temperature. The zero is arbitrary, and what this means is that we cannot use Fahrenheit and we cannot use Celsius in any gas calculation that we have. Never, ever, ever. And I'll show you why in just a second, but you can never use Fahrenheit or Celsius in any gas calculation. We need a different scale. We need a scale where the zero on that scale is actual thermodynamic zero, that the particles are moving as slowly as they can. They can't go any slower. And the scale we're going to use in this is basically called the Kelvin scale. And so Kelvin is an absolute temperature scale. And so we just say K. We don't say degrees K, just K. And so, you'd say, if you say 32 degrees Celsius, but you'd say 32 Kelvin. No degrees whatsoever. And so, never degrees K right there. In this class, and in fact, in general, you're always going to use Kelvin in any gas calculations. If it says temperature, use Kelvin. If it gives it to you in Fahrenheit, you got to convert it to Kelvin. You have to use Kelvin. I can't really say that enough. That if you use something else, your calculation will be wrong. Zero in the Kelvin scale is what's called absolute zero. There's no way to get any lower. It is as slow as the particles can go. The lowest energy that those particles can have. They can't get any lower. And so as a result, basically, it'll correspond to the lowest possible pressure. And so because the particles are moving as slowly as they can, they'll hit the walls as slowly as they can, and they'll put the least possible force and therefore having the least possible pressure. And so we're always going to have to use the Kelvin scale. But how do we know what to use on the Kelvin scale? If I'm given a temperature and I'm told it's 56 degrees Celsius, what is that in Kelvin? We need to be able to convert. And so that's what we'll look at next. How do we convert? And so to do that, let's take a look at a scale here. What we've got here are some nice things. We have the boiling point, the freezing point, absolute zero for our three temperature scales, Fahrenheit, Celsius, and Kelvin. And so to start with, let's start with a freezing point. And so for freezing point from the Fahrenheit scale is simply 32 degrees. Freezing point on the Celsius scale is 0 degrees, like that. And we'll worry about Kelvin in a little. Well, actually, we'll go ahead and do this here. The freezing point on the Kelvin scale is 273.15 Kelvin, right there. The boiling point of water on Fahrenheit is 212 degrees. The boiling point in Celsius, as we've sort of talked about before, is 100 degrees Celsius. And the boiling point in Kelvin is 373.15 Kelvin. And so these are basically our boiling and freezing points. Absolute zeros. For Kelvin, it's easy. Absolute zero in Kelvin is 0. Oops. No, that's bad. Never put degrees on Kelvin. That's my mistake there. On Kelvin, it's 0K. 0 Kelvin. Absolute zero is easy here. For Celsius, if you're paying attention, you can actually probably figure it out here. Look at the difference between boiling and freezing on Celsius. It goes from 0 to 100. There's a difference of 100. Look at Kelvin. We go from 273.15 to 373.15. Difference of 100. 1 Celsius degree and 1 Kelvin are the same size. They have different zeros. They start at different places, but they're the same size. And so if the difference in Kelvin between the absolute zero and the freezing point of water goes from 0 to 273, the difference is 273. That means in Celsius, the difference also has to be 273.15. And since we start at 0, it means in Celsius, absolute zero is negative 273.15 degrees Celsius. Okay? In Fahrenheit, it's actually roughly negative 460. That's 460 degrees Fahrenheit is absolute zero there. And so really, really low here. Now, to be able to find conversions here, what we're going to look at is the difference in temperatures. We already said that the difference on Celsius is 100. There are 100 Celsius degrees that are basically between freezing and boiling. For Fahrenheit, if we look at those, then we go 212 minus 32. What you get is 180 degrees. And so every 100 Celsius degrees is equivalent to 180 Fahrenheit degrees. And so if you think about it, that means we have a sort of a ratio. The ratio here would be 180 over 100. And so this reduces down to simply 9/5. And so that means that 1 Celsius degree is 9/5 the size of a Fahrenheit degree. this fact is going to let us do some conversions here. And so let's take a look at what those conversions would be. Come on. All right. So first thing, Celsius to Kelvin and Kelvin to Celsius. Very straightforward. We said the difference, they're the same size degree. They're just shifted off by 273.15. So to go from Celsius to Kelvin, all we have to do is we take the Celsius temperature and add 273.15. That gets us Kelvin. So 0 Celsius would be 0 plus 273.15, 273.15 Kelvin. 20 degrees Celsius would be 293.15 Kelvin. Just like that. We're going to go from Kelvin to Celsius. You do it in reverse. You take the temperature in kelvins, subtract off 273.15. And so if I have 300 Kelvin and I want to know what that is in Celsius, I'd say 300 minus 273.15. And so I get, what is that, 26.85 degrees Celsius would be what that would be right there. Celsius to Fahrenheit. This one gets a little more complex. Remember we found this 9/5? There it is right there. And so to convert from Celsius to Fahrenheit, you take the Celsius temperature and multiply it by 9/5, and then you add 32. Because there's a difference of 32 Fahrenheit degrees between basically 0 Celsius and 0 Fahrenheit. And so let's sort of a quick double check here, is we know this. We know that 100 degrees Celsius is 212 Fahrenheit. They're both the boiling point of water. So if you take 100 Celsius, put it in for this one, you take 9/5 times 100. 9/5 times 100 is 180. 180 plus 32 gives us a total of 212. Excellent. Right like we want it to be. So that works out. Fahrenheit to Celsius, we do the same thing. Is we sort of flip it around. This time instead of 9/5, it's just 5/9. We take the Fahrenheit temperature, subtract off 32, multiply it times 5/9. So we know that 0 Celsius and 32 Fahrenheit should be the same. So let's put in 32 for Fahrenheit. So Fahrenheit is 32, minus 32 gives us 0. 0 times 5/9 is 0. So 32 Fahrenheit is 0 Celsius, which we know to be correct. And so these are your temperature conversions. Want to have these written down on a colored sheet somewhere, unless you have them memorized. And we'll need to do these in order to convert. Let's try out some examples and make sure we can get this to work here. Question is, what is 54 degrees Fahrenheit in Celsius? So we have Celsius. We want to find what this is. We say the conversion for Celsius is going to be this guy right here, Fahrenheit to Celsius. So Celsius is equal to 5/9 times the quantity of Fahrenheit temperature, which is 54, minus 32. And so if you get out your calculators here, then what we can do is we can say that 54 minus 32 is 22. And the 22 times 5/9 gives us 12.2. And so 54 degrees Fahrenheit would be equal to 12.2 Celsius. Now significant figure-wise, we have two sig figs here. So the answer would simply be 12 degrees Celsius. And so that would be our answer there. Another possibility, what's 17 degrees C in Kelvin? And so in this case, we're looking for Kelvin. And so since we're looking for Kelvin, we're going to do our Celsius to Kelvin conversion. And so we'll say that Kelvin is equal to Celsius plus 273.15. So 17 plus 273.15. And so when we do that we're going to end up getting here, see, what would that be? So 17 plus 270 is 290.15. And so we have two significant figures. So 290 Kelvin is what we're going to have here. And so that's going to be our final answer here. Now, a couple sort of quick notes about significant figures. Still, for the purposes of this class, we're going to assume that temperatures are rounded to the ones place. So 30 degrees C would have two significant figures. Technically doesn't, but we're going to assume that. The 273.15, that's considered to be exact for what we're doing here. So if I told you that this was actually 17.3895287, is that still that 17.32857 or whatever it was right there is going to determine significant figures. The 273.15 will never determine significant figures because of the fact we're considering that to be exact. So 290K is what we get. And so that one we do have to round to two significant figures because of the fact we had 17.2 to start with. Last one, what's 300K in Fahrenheit? We don't have a Fahrenheit to Kelvin or Kelvin to Fahrenheit conversion. So what we're going to have to do is convert first from Kelvin into Celsius and then go to Fahrenheit. And so we know that Celsius is Kelvin minus 273.15, right up there. And so we say 300 Kelvin minus 273.15. And so doing that, we get a Celsius temperature, let's see, 273.15, subtract that off, we get 26.85. 26.85 degrees Celsius. No rounding yet because we're not done with this. Now we want to get to Fahrenheit. We know that our Fahrenheit conversion is right over here, is equal to 9/5 times Celsius, which is 26.85, and then plus 32 on that. And so we take our 26.85 times 9/5, and then we'll take that answer plus 32, and so we get 80.33. And so to one significant figure, that's just 80 degrees. And so our Fahrenheit temperature would be 80 degrees Fahrenheit. And that's how we set that up. And so that's our final answer. 300K is 80 degrees Fahrenheit. Though actually, I sort of forgot about that. Actually, this should have 3 significant figures, not 2, because remember we said we round these to the nearest degree. And so this should actually not be 80, it should be 80.3. I'm sorry about that. So 80.3 degrees Fahrenheit, because we said, as we said before, is that we're going to round temperatures to the nearest degree, and so we have 1, 2, 3, the nearest degree there. Just for the purposes of this class. It's not a general, it's not an outside rule, it's just one we do in here to keep things simple. Let's take a look at another one of our temperature laws. Charles's law. So we already talked a little bit about this, but if you heat up the air in a hot air balloon, what happens to the volume? Well, we know this. If we heat up the air in a hot air balloon, it's going to give the particles more energy, so they're going to move faster, so they're going to hit the walls harder. If they hit the walls harder, then we'd expect that the balloon's going to expand. And so that we would say then that as the temperature goes up, we could expect that the volume would also go up, which means these two are directly proportional to each other. And if they're directly proportional to each other, the equation we have to use is the one that you see on your screen here. This is Charles's law. V1 over T1 equals V2 over T2. This works exactly the same way as Boyle's law did, in that V1 and T1 are the original volume and the original temperature, and V2 and T2 are the final volume and the final temperature. Same as before, we can use whatever unit of volume we want to. So V1 could be in liters, and if V1 is, then V2 has to be in liters. V1 could be in gallons. If it is, V2 has to be in gallons. V1 can be in cubic centimeters. If so, V2 has to be in cubic centimeters. However, as we said in the previous section, the temperature has to be in Kelvin. Always in Kelvin. You have no choice on this matter. Is that if you are given the temperature in Celsius, you have to convert it to Kelvin first. And only Kelvin can be used for your temperatures here. And so if I were to say something like, if we know that we have a 3-liter container at a temperature of 30 degrees Celsius, then the temperature is taken up to 60 degrees Celsius. The question is, what is the volume? One, we're going to have units of liters, but what we're going to have to do here is we say the original volume, V1, is 3 divided by the original temperature. We cannot use 30 degrees Celsius. We're going to have to convert it to Kelvin. To convert it to Kelvin, we add 273.15, so we get 303.15. And then this is going to be equal to the V2, the volume afterwards, we don't know, times the temperature afterwards, which will be we cannot use 60 degrees Celsius because it's Celsius. It has to be Kelvin. So we have to add that to 273.15, and so we get 333.15. And so if we go ahead and set this up, then we'd say, basically, let's see, 3 divided by 303.15, and then times 333.15. And doing that, I get 3.296. And so the volume that we'd get here for V2, significant figure-wise, I had just 1 for my 3 liters to start with here. And so we'd have only 1 here, so we'd actually just get 3. And so 3 liters. There wasn't a whole lot of change in the volume. To if we didn't worry about significant figures, we get 3.3 basically. And so you can see there was a change in the volume here. It was just less than what we could tell based on the significant figures that I gave you here. So the final answer that you need to put down would be 3 liters. But so it really doesn't change that much between 30 and 60 degrees Celsius. But you can sort of see that we have to use Kelvin. Those Kelvin temperatures are mandatory. No choice on that. So let's look at another example of how we might work out one of these guys. And so let's take a look. So the balloon with a volume of 2.2 liters at 20 degrees C is heated at 90 degrees C. What's the new volume of the balloon? And so to do this, we know that we have the original volume. V1 is 2.2 liters. The original temperature, T1, is 20 degrees C. The final volume, V2, we do not know. That's a question mark. The final temperature, T2, is 90 degrees C. Okay, so we're going to set up Charles's law. And so V1 over T1 equals V2 over T2, like that. And so doing this here, V1 is 2.2 liters over the temperature. Temperature T1 is 20 degrees C. We can't use 20 degrees C. We're going to have to instead replace that with that in Kelvin. And so Kelvin would be 20 plus 273.15, so we get 293.15 Kelvin. So that's what we have to use here, 293.15 Kelvin. Okay? And so continuing with this is that this is going to equal to V2, which we don't know, over T2. T2 is 90 degrees C. Can't use that there. And so we're going to have to convert 90 degrees Celsius into Kelvin. And so 273.15 plus 90 equals 363.15. I'm doing my math right. Kelvin. So we put in 363.15 Kelvin is what we get for this. And so now we're going to go ahead, set up, and solve this. And so solve for V2. And so we say 2.2 times 363.15 divided by 293.15. And so I get 2.72 for V2. Significant figures, looking at what we've got here, we have 2 here. Since this goes to degrees, that's 2. This goes to degrees, that's 2. So our answer should have 2. So our final answer for V2 is going to be 2.7. Units are going to be the same as what we had over here. And so in this case, that's going to be liters. So 2.7 liters is our final answer. And so that went from 2.2 liters to 2.7 liters by heating it up. One last gas law. We have talked about what happens with pressure and volume and temperature and volume, but we have not talked about is pressure and temperature. This is Gay-Lussac's law. And so Gay-Lussac's law basically sort of says this. Let's suppose that we have a water bottle. We heat up the air inside the water bottle. What's going to happen to pressure? If we heat up the air in the water bottle, the particles are going to move faster. If the particles move faster, they're going to hit the walls with a harder force. If they hit the walls with a harder force, then it means we're going to have a higher pressure. And so we know that pressure and temperature then, if we increase the pressure or we increase the temperature, we increase the pressure, and vice versa. And so they're directly proportional. And so Gay-Lussac's law says P1 over T1 equals P2 over T2. Same rules apply as did before. P1 and T1 are the original pressure and the original temperature. P2 and T2 are the final pressure and the final temperature. P1 and P2 can be in any unit of pressure that's acceptable as long as they're the same unit. If P1 is in torr, P2 has to be in torr. P1 is in atmospheres, P2 has to be in atmospheres. Any units as long as they're the same on both sides. Temperature, though, once again, must be in Kelvin. Can't be in Celsius, can't be in Fahrenheit, can't be in Rankine, which is another degree temperature scale that's used sometimes. It has to be in Kelvin. Actually, I guess it could be in Rankine, but we're not going to talk about that. We'll say for this class, has to be in Kelvin. So this is it right here. So let's do one example here. It works very much the same way as our previous ones did. So a tire is filled to 33 psi, pounds per square inch, when the temperature is 0 degrees C. If the temperature rises to 30 degrees C, what is the pressure in the tire? So let's set this up, is that we have P1, the original pressure. In this case, is 33 pounds per square inch, 33 psi. Not a normal pressure unit, but we said it's acceptable to use any pressure unit as long as it's the same before and after. So we should be good here. The original temperature is 0 degrees C. Okay, so we got that. The final pressure, P2, We don't know what that final pressure is. The final temperature, T2, in this case is going to be 30 degrees C. So let's set up Gay-Lussac law. So P1 over T1 equals P2 over T2, like that. And so the original pressure in this case is 33 psi over the original temperature, but the original temperature is in Celsius, so once again we can't use that. We'll have to convert. So we add 273.15 to 0, get 273.15 Kelvin. And then once we've got that, is that we set up the rest of the equation, equals P2, we do not know what that is, over T2. T2 is 30 degrees Celsius, but 30 degrees Celsius is not in Kelvin, so we have to add 273.15, and we get 303.15 Kelvin. So P2 is 303.15 Kelvin. And now it's just a matter of putting it into the calculator and solving. And so we take 33 divided by 273.15, and then we take that and multiply it by 303.15 to solve for P2. And so when you do that, is you end up with a P2 of 36.624. Significant figure-wise, we have two significant figures here. This guy looks like one, but since that's sort of exact, it's exactly 0 C's here. When we converted this over, it became 273.15, which we're not going to affect. It'll basically be, okay. Since we added these two, we said in order to find the 273.15, we had to add 0 to that. 0 has one significant figure to it in this case. We added 273.15 means it's going to be rounded to the ones place here. And so that means we'll have three significant figures from this temperature. Same thing from this temperature right here. Since 30 would be rounded to the ones place, this will be three significant figures. And so our answer will have 2 for our final one. Remember your addition significant figure rules. We don't use those very often. But so if you do that, you end up with 37. And so our final answer here is 37. The unit is PSI because the original unit was PSI. We can use any unit of pressure we want to as long as it's the same on both cases here. And so going from 0 degrees C, it's about 32 degrees Fahrenheit, to 30 degrees C, which is up a pretty high temperature. That's like hot summer temperature right there. It would go from 33 PSI to 37 PSI just by increasing the temperature. And that goes over your basic gas laws. And next time, we will look a little bit at what happens when we have not just pressure and temperature changing, but we have all three changing all at the same time.